Welcome! In this session, we'll be tackling problem number 1209, titled Remove All Adjacent Duplicates in String 2. Together, we'll explore the problem, break it down step by step, and analyze effective strategies to solve it. Let's dive in. In this problem, you are given a string s and an integer k. The goal is to remove all adjacent duplicates from the string, where an adjacent duplicate is defined as k or more consecutive characters that are the same. When you remove such duplicates, new ones might form, and these also need to be removed. This process is repeated until no further duplicates remain. The final result is a string with all such adjacent duplicates removed, and it is guaranteed that this resulting string will be unique. For input, you are provided with the string s, which consists of lowercase English letters, and an integer k that determines the threshold for removing duplicates. The output will be the final process string after all duplicate removals are complete. Let's consider some examples to better understand the rules of this problem. In the first example, the input string is s equals abcd and k equals 2. Since there are no adjacent duplicates of length 2 or more, no characters are removed. Therefore, the output remains the same as the input abcd. This example highlights that when no duplicates meet the threshold of k, the string remains unchanged. For the second example, we have s equals ddkukvet and k equals 3. Here, there are adjacent duplicates that meet the threshold, so the string will be processed step by step to remove them. Let's see how this unfolds. For s equals ddkukvet and k equals 3, the first group of adjacent duplicates is e, which is removed, leaving dkukavda. Next, the group BBB is removed, resulting in dekta. Then, CCC is removed, yielding da. After that, DD is removed, leaving AA. At this point, no further duplicates of length 3 exist, so the final output is AA. This example illustrates how the removal process works iteratively, eliminating duplicates until the string stabilizes with no further changes. Now let's explore a slightly more complex example. In the third example, the input is s equals psitsipoepois and k equals 2. First, the substring bb is removed, leaving psitsipoepoes. Then, gg is removed, resulting in ptiapoepoes. Next, tt is removed, giving psiapos. The group 2 is then removed, leaving ppois. After that, pp is removed, producing poais. The sequence oo is removed next, yielding pais. Then, AA is removed, leaving CPS. Finally, the last group of AA is removed, resulting in PS. This example demonstrates how the process can involve multiple steps and how duplicates at different positions are removed in sequence to produce the final string. When solving this problem, there are several edge cases to consider. For instance, if the string contains no adjacent duplicates of length k, the output will simply be the original string. If k equals the length of the string and all characters are identical, the entire string will be removed in one step. Another important scenario is when the string is very large, close to the maximum constraint of 10 to the power of 5 characters. In such cases, the solution must be efficient to handle the input within a reasonable time. Lastly, if the string consists of a single repeated character, the entire string will be removed as long as its length is divisible by k. These edge cases highlight the importance of carefully considering input constraints and ensuring the solution efficiently handles all scenarios. To solve the problem of removing all adjacent duplicates in a string with k consecutive characters, the brute force approach provides a straightforward but inefficient solution. The idea here is to repeatedly traverse the string, looking for any group of k identical adjacent characters, and remove them. This process is repeated until no such groups are left. While this method is easy to understand and implement, it has significant drawbacks. Each traversal requires a scan of the entire string, and because strings in languages like Python or Java are immutable, every modification essentially creates a new string. This leads to a time complexity of n squared, in the worst case, as the string is processed multiple times. Additionally, while the space complexity is 1 for auxiliary space, the cost of creating new strings adds overhead. This makes the brute force approach unsuitable for large inputs, as it becomes computationally expensive and inefficient when handling long strings or frequent duplicates. To improve upon the brute force method, we can use a stack-based approach that is far more efficient. The key insight here is that instead of repeatedly scanning the string, we can process it in a single pass by leveraging a stack. In this approach, the stack is used to track characters and their consecutive counts. Each stack element is a pair consisting of a character and its current count. When processing the string, if the current character matches the top of the stack, we simply increment the count. If the count reaches k, we pop the element from the stack to remove the group of duplicates. This eliminates the need for repeated scans of the string. The stack allows us to maintain a running record of characters and their counts, making the process both efficient and easy to manage. By the end of the traversal, the stack contains only the characters that remain after removing all adjacent duplicates. Here's how the stack-based approach works step by step. First, we initialize an empty stack. Then, we traverse the string character by character. For each character, we check if the stack is non-empty and if the top of the stack matches the current character. If it does, we increment the count for that character. If the count reaches k, we pop the stack, which effectively removes the group of adjacent duplicates. If the character doesn't match the top of the stack, or if the stack is empty, we push the character onto the stack with a count of 1. Once the traversal is complete, the remaining characters in the stack are used to reconstruct the final string. This approach is highly efficient, with a time complexity of O(n), since each character is processed exactly once, and stack operations like push and pop are constant time. The space complexity is O(n) as well, due to the stack storing elements for the worst-case scenario, where no duplicates are removed. The stack-based approach is the clear choice for this problem due to its efficiency and simplicity. Unlike the brute force method, it avoids the need for repeated scans and excessive string manipulation, which makes it highly suitable for handling large inputs. The key insight here is that the problem can be reduced to maintaining a stack that tracks consecutive duplicates and their counts, allowing us to eliminate groups of duplicates in a single traversal. This realization not only improves performance but also simplifies the implementation. The stack-based method is efficient, with a linear time complexity of O(n), making it significantly faster than the O(n²) brute force alternative. It is also scalable, as stack operations are lightweight and the approach handles large strings effectively. While the space complexity is O(n), due to the stack, this is a minor trade-off compared to the substantial performance gains. Overall, the stack-based approach strikes an excellent balance between time efficiency, space usage, and ease of implementation, making it the optimal solution for this problem. To solve this problem, we need to repeatedly remove groups of k consecutive identical characters from a given string until no such groups exist. For example, if the input string is d and k equals 3, we remove groups like e and ccc, eventually returning the final string aa. To achieve this efficiently, we use a stack data structure. The stack helps us keep track of characters and their consecutive counts. For instance, if we encounter the string ab, the stack would record a2, b2. This way, we can group and process characters incrementally without rescanning the entire string. As we iterate through each character, we check the top of the stack. If the current character matches the one at the top, we simply increment its count. Otherwise, we push the character onto the stack with an initial count of 1. This approach ensures that we always have the most recent character group at the top of the stack for quick access. Once we update the count for a character in the stack, the next step is to check if the count has reached k. If it has, this means we've identified a complete group of k consecutive characters, so we remove the top element from the stack. This removal simulates deleting the group from the string. After processing all characters, we reconstruct the final string by traversing the stack. For each character in the stack, we multiply it by its count and concatenate the results. This gives us the desired output without redundant processing. The stack-based approach is highly efficient because it avoids repeatedly scanning the string to find groups, as would be the case in a brute force method. Each character is processed at most twice, once when added to the stack and possibly once when removed. This makes the algorithm run in linear time, or O(n), where n is the length of the string. The space complexity is O(n) in the worst case, such as when all characters are unique, though typically it will be less as groups are removed. Handling edge cases is crucial for ensuring our algorithm works reliably across all scenarios. For example, if k is larger than the length of the string, no groups can ever form, so the result is simply the original string. Similarly, if the input string is empty, the output will also be an empty string. Another interesting edge case occurs when k is equal to 1. Here, every single character forms a group of size 1, so the entire string will be removed, leaving an empty result. To implement this effectively, we rely on the stack data structure, which continues to store pairs of characters and their counts. The stack evolves as we iterate through the string. For instance, with the string a, the stack progresses step by step. Starting with the stack first holds a1, then a2. When we move to b, it becomes a2, b1, and then a2, b2. Finally, for c, it updates to a2, b2, c1, and then a2, b2, c2. This systematic grouping ensures that we can efficiently identify and remove duplicates as needed. To optimize further, we avoid building intermediate strings during the process. Instead of creating new strings after every removal, we directly use the stack to accumulate results. This reduces overhead and improves performance. The final implementation in Python follows this approach. We define a function remove_duplicates that takes the string s and integer k as inputs. The function initializes an empty stack to store pairs of characters and their counts. As we iterate through the string, we check whether the stack is non-empty and whether the current character matches the one at the top. If it does, we increment its count, and if the count reaches k, we pop it from the stack. Otherwise, we add the character to the stack with a count of 1. After processing all characters, we reconstruct the result by concatenating each character in the stack multiplied by its count. For example, given the string d and k equals 3, the function outputs AA, as all groups of size 3 are removed. This implementation is efficient, clear, and leverages the stack's properties to solve the problem in linear time. The solution uses a stack-based approach to efficiently remove adjacent duplicates in the string until no valid groups remain. The remove duplicates function takes two parameters, s, the input string, and k, the number of consecutive duplicates required to form a removable group. Step-by-step explanation. 1. Initialize the stack asterisk. The stack is used to keep track of characters and their consecutive counts. Each entry in the stack is a pair, char, count. 2. Iterate through the string asterisk. For each character char in the string. If the stack is not empty and the top of the stack contains the same character, increment the count for that character. If the count reaches k, this group of k characters is removed by popping the top of the stack. If the current character is different from the top of the stack, add a new entry, char, 1, to the stack. 3. Reconstruct the result asterisk. After processing all characters, the remaining characters and their counts in the stack are used to reconstruct the final string. This is done using a list comprehension to repeat each character by its count and joining the results. Efficiency. The algorithm runs in O(n) time, where n is the length of the string. Each character is pushed and popped from the stack at most once. The space complexity is O(n) in the worst case, depending on the size of the stack. This solution handles all edge cases, including strings with no removable groups, strings where multiple rounds of removal are required, strings with varying group sizes. Overall, this approach is efficient and robust for the given problem constraints. Here, we start with the implementation of the solution in Java. First, we import the required utility package and define the main class solution with the method removeDuplicates. This method takes two inputs, the string s and an integer k, which represents the number of adjacent duplicates required to trigger removal. Inside the method, we use a stack to store pairs of characters along with their counts. The stack helps us efficiently track and manage groups of adjacent duplicates as we iterate through the string. For each character in the string, we check if the stack is not empty and whether the character at the top of the stack matches the current character. If it does, we increment the count of the top pair. If that count reaches k, we remove the pair from the stack, effectively removing the group from consideration. Otherwise, if the current character doesn't match the one on top of the stack, we push a new pair with the current character and a count of 1. This ensures that we always maintain a record of the current sequence of duplicates being processed. Finally, we use a string builder to reconstruct the output string from the characters and counts remaining in the stack. The for loop completes the reconstruction of the result string by appending each character from the stack the appropriate number of times, based on its count. Once the string is fully built, we return it as the final result. Additionally, we define a helper class named pair to simplify the handling of characters and their associated counts within the stack. This class contains two fields, character, which stores the character itself, and count, which stores the number of times the character has consecutively appeared. The constructor initializes these fields whenever a new pair instance is created. By using this helper class, the implementation remains clean and easy to understand. The combination of the stack-based approach and the pair class ensures that the solution is both efficient and intuitive, neatly handling the removal of adjacent duplicates while reconstructing the output string in the correct order. To solve this problem, we use a stack to efficiently track groups of adjacent duplicate characters. Starting with the first example where the input string is ABCD and k equals 2, we begin by initializing an empty stack. As we process the first character, we notice the stack is empty. This means there's no duplicate to check, so we append it to the stack along with a count of 1. Next, we move to the character B. Since the top of the stack contains a, which is different from B, we simply append B with a count of 1. Similarly, for the character C, because it differs from the top of the stack, which is B, we append C with a count of 1. Lastly, we process D, which also differs from the top of the stack, so we append it with a count of 1. At the end of this process, the stack contains a, 1, B, 1, C, 1, D, 1, and no adjacent duplicates are found. Now, we reconstruct the string from the stack. Each character in the stack is repeated according to its count, which results in the original string ABCD. Since no adjacent duplicates of size k were found, the string remains unchanged. Moving to the second example, where the input string is d and k equals 3, we start by initializing an empty stack. The first character, D, is processed, and since the stack is empty, we append D with a count of 1. Next, we process E. As E is different from D, we append E with a count of 1. When we encounter another E, we increment the count of E in the stack to 2. This count represents the number of consecutive E characters seen so far. As we process the next E, we increment its count to 3. Since this matches K, we remove E from the stack, effectively eliminating this group of adjacent duplicates. The stack now only contains D1. We then process another D, incrementing its count to 2. After that, we encounter B, which differs from the top of the stack, so we append B with a count of 1. For the next 3 C characters, we increment the count of C in the stack to 3, and as this matches K, we remove C from the stack. This leaves us with D2, B1. Next, we process another B, incrementing its count to 2. At this point, the stack is D2, B2. Finally, we process 2 A characters. Since it is new to the stack, we append it with a count of 1 and then increment the count to 2 as we process the second A. The stack now looks like D2, B2, A2. To reconstruct the string, we repeat each character in the stack according to its count, which results in AA. In the third example, with the input string puktsitsipoepois and k equal to 2, we follow the same process. After processing all characters and repeatedly updating the stack, we end up with P1, C1, I1, A2, S1. Reconstructing the string from the stack gives us PS. This demonstrates how the stack helps efficiently remove adjacent duplicates in groups of size k. The time complexity of this solution is O(n), where n is the length of the input string. First, we iterate through the string one character at a time. This traversal is done exactly once, so it contributes O(n). Next, the push and pop operations on the stack are efficient, each taking O(1) time. Every character in the string is pushed onto the stack and possibly popped at most once, which means the total stack operations for all characters also contribute O(n). Together, these operations ensure that the traversal and stack management are linear with respect to the size of the input. Once the input string has been fully processed, we need to reconstruct the final result. This involves iterating over the stack, which contains up to n/k entries in the worst case, since groups of k adjacent duplicates are removed during processing. For each entry in the stack, we multiply the character by its count to form the final string. This reconstruction step is also linear, contributing O(n). Adding up the traversal, stack operations, and reconstruction, we get O(n) plus O(n) plus O(n), which simplifies to O(n) overall. For space complexity, we consider the stack, which stores character count pairs. In the worst case, all characters are stored in the stack, requiring O(n) space. The space complexity also accounts for the result string, which is constructed from the stack. Since the length of the result string is proportional to the input string, this adds another O(n) for space. Finally, there is no significant auxiliary space usage, as operations such as append, pop, and join are performed in place. Combining the space required for the stack and the result string, the total space complexity remains O(n). This ensures that our solution is efficient in both time and space usage, even for large inputs. To understand the efficiency of this solution, let's compare it with a naive approach. A brute force method would involve repeatedly scanning the string to remove adjacent duplicates of size k. Each scan takes O(n) time, and in the worst case, this process could repeat up to n/k times. This leads to a time complexity of O(n)(2/k), which is significantly less efficient than our optimized solution. By contrast, the stack-based approach processes each character only once, avoiding repeated scans. This brings the time complexity down to O(n), making it far more suitable for large strings. Now let's analyze the best, average, and worst-case scenarios. In the best case, all groups of size k are adjacent and removed during the first traversal. This means the solution achieves O(n) time complexity with minimal stack usage, leading to an effective space complexity of O(1). In the average case, groups of k are distributed throughout the string, but the reduction happens progressively. Here, the time complexity remains O(n), and the space complexity is O(n) due to the stack. In the worst case, no groups of size k are removed, meaning all characters are stored in the stack. Even in this scenario, the time complexity is O(n), and the space complexity is O(n). To formally prove the big O complexity, consider the time complexity first. Each character is pushed and popped from the stack at most once, resulting in O(n). Additionally, reconstructing the final string from the stack involves iterating through its entries, which is another O(n). Combining these, the total time complexity is O(n) plus O(n) equals O(n). For space complexity, the stack can grow up to O(n) in the worst case, and the result string also requires O(n) space. Therefore, the total space complexity is O(n), confirming that the solution is both time and space efficient for the given problem. One common mistake when solving this problem is not accounting for overlapping groups of duplicates. For instance, consider the string AUBK. If you remove the first group, AAA, you now expose another group, BBB, which also needs to be handled. Your solution must be designed to rescan and handle these newly formed groups effectively. Another pitfall is using inefficient brute force methods that repeatedly scan the entire string after each removal. This approach can quickly lead to poor performance, especially for large inputs, as it often results in a time complexity of O(n)² or worse. A stack-based approach is typically more efficient. Additionally, edge cases are often overlooked. Scenarios like when k is greater than the length of the string, or when the string contains no groups of k identical characters, need to be carefully tested. For example, an empty string or a string made up of entirely unique characters should be handled gracefully. Lastly, in languages like Python, repeatedly modifying immutable strings can lead to inefficiencies. Using a list to simulate stack operations is generally a better choice. It's also important to fully understand the role of k in the problem. Assuming k is always 2 may third work for some cases, but it's not a reliable approach for all inputs. Now, when discussing this problem in an interview setting, it's important to focus on a few key insights. First, recognize the pattern in problems like this one. Group removal often aligns naturally with stack-based solutions, so identifying this can guide you toward an optimal approach. Efficiency is another critical factor. While brute force may work for smaller inputs, interviewers are generally looking for candidates who can implement an O(n) solution. Using a stack demonstrates your ability to optimize performance. It's also important to emphasize how your approach handles intermediate states, such as what happens after each removal. This shows that you understand the problem's iterative nature. Finally, take the time to ask clarifying questions at the beginning of the interview. For instance, understanding constraints like the maximum string length and valid values of k can help you tailor your approach. If the constraints are lenient, brute force might be acceptable, but for larger inputs, efficiency becomes critical. There are also several related problems on LeetCode that can help you strengthen your understanding of similar concepts. For example, problem 1047, remove all adjacent duplicates in string, is a simpler variation of this problem. Problem 726, number of atoms, and problem 316, remove duplicate letters, both involve stack-based string manipulation and can deepen your familiarity with stack operations in different contexts. When it comes to alternative approaches, the stack-based method stands out as a robust solution. Here, you maintain a stack to track characters and their counts. If a character's count reaches k, you pop the group from the stack. This approach is efficient, with a time complexity of O(n) and a space complexity of O(n), and it avoids the inefficiencies of rescanning the string. While it requires a solid understanding of stack logic, it's highly optimal for this type of problem. Another approach to solving this problem is the two-pointer technique. This method involves using 2 pointers to identify and remove groups in a single pass, which can reduce overhead and achieve O(n) time complexity with O(1) space complexity. However, it's a bit more complex to implement, especially when handling overlapping groups efficiently. A third option is the recursive approach, where you repeatedly remove groups of k characters until no groups remain. While this method is conceptually simple and easy to implement, it has significant drawbacks. Its time complexity can degrade to O(n²), in the worst case due to repeated slicing of the string, making it unsuitable for large inputs. Each of these approaches has its trade-offs, so it's crucial to weigh efficiency against implementation complexity when deciding which one is best suited for your needs. Great work! We've summarized the problem and key strategies for solving it. Remember, practice makes perfect. Keep honing your skills, and we'll see you again soon. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!